Hello class, today we're going to be talking about significant figures and scientific notation. First off, let's talk a little bit about scientific notation. Alright. We use scientific notation for very small numbers and also very large numbers. I know my class found this out when we did our aluminum foil activity today, that we had some very small numbers, especially dealing with pico or mega.
Right. Right, so we can write these numbers out, these really small numbers, using all of these zeros, and I know that a lot of you in my class were writing out a whole bunch of digits. And so today, that's our main topic, is we're going to tell you how to get rid of all of these digits and which ones are important, which ones are not. Okay, so all of our answers from now on in chemistry need to be expressed in scientific notation. You can't just have a number that isn't expressed in scientific notation. It's just not thought of as being correct. So to do that, we would move our decimal place over. So this would be technically where our decimal place would be, and we'd move it over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So this number would be 6.02 times 10 to the 14th. And notice I put that decimal right there because that's one of our rules that we're going to talk about later, that this first number has to be between 1 and 9. You can't have two digits. No. And then, of course, we can do it for a very small number, and we would go back 1, 2, 3, 4, 5, 6, 7, 8, 9. We'd want to stop right there, so we'd have one number, then the digit, or then the decimal. So it'd be 4.35 times 10 to the negative 9. Negative means that it is small.
Small, very small number.
Okay, so how come I guess I just kind of lopped off all of these zeros? Did you notice that?
Yeah, I did.
Because I guess this would still be correct, wouldn't it?
Yes.
That would still be okay?
No, it would not.
I mean, that's still the same number, though.
Right.
Right. But, I mean, when do we stop? How do we know?
Because we have rules for significant figures.
Significant figures, which is our next slide. Significant figures. So no more rounding.
No more rounding. We're going to get rid of the zeros.
No more, hey, Mr. Fitzsimmons, what do I round this to?
Nope, you will know, and you will have a set of rules to follow for every answer that you get.
Right? This is the only way to express your answer correctly, is by using significant figures. All of a sudden, those zeros at the end, so if you have 2.70, this zero is extremely important.
Right.
All answers must have correct significant figures for full credit on your test. So we're going to tell you what they are, obviously, and in order to get full credit, you'd have to have the right amount. Significant figures for an answer, this is a very interesting sentence here, depend on the number of sig figs in the question. Okay, so this really right here, hopefully you can look back on this bullet later and really understand what that means, because there's not a set rule for just all answers. It's going to be question dependent.
Yeah.
Okay, so let's go ahead and look at our rules for significant figures.
All right.
Okay.
Our first rule is that non-zero numbers are always significant. Okay. Non-zero numbers are always capitalized, always significant.
Okay, and so what does that mean exactly? Non-zero numbers.
You know, any number from 1 through 9 that we have.
Okay, so how about like this? Are all those significant?
Those would all be significant numbers. 1, 4, 2, and 1. All significant.
And how many significant numbers are there?
There are 4 in that number.
Okay, so how about this number?
There are 2, because both 1 and 2 are significant.
Right.
And they're both non-zero numbers.
Perfect. We'll come back to that. Maybe do a couple more examples.
Okay.
After we get into the confusing stuff.
The more confusing
Just kidding.
stuff.
It's not.
Okay. Second rule we have, zeros between non-zero are always significant. Zeros between non-zero are always significant. No. Just giving us a challenge.
That's right. Significant. Okay, so what would be an example of this?
If we had the number 60.23, all right, we have a 0. All right. Don't be confused by our first rule. All right. Saying that non-zero numbers are always significant. Don't think that that 0 is not significant. Okay. In this number, there are actually 4 significant figures. Okay.
Because that zero's between non-zeros. So since this is a non-zero number and this is a non-zero number, this guy automatically becomes significant.
Yes.
Okay, cool. Let's go to the next one.
Our third rule, all right. All final zeros to the right of the decimal are significant if there is a number in front. And I'll repeat that. All final zeros to the right of the decimal are significant if there is a number in front. All final zeros are significant. The number in front of the decimal.
Okay, so what would be an example of this guy?
6.200. Okay.
So since we have a decimal here and there's a number in front of it, that means all these zeros are significant. And mind you, this is before scientific notation.
Right.
Oops. Sci Not. I call these Sig Figs and Sci Not. So on that earlier slide that we just did, right here, so the decimal's right here, okay? And so these zeros behind it, there isn't any zeros. Okay, here, I put zeros in, and there's a number here, but it's already in scientific notation, so this wouldn't count. So these zeros are insignificant here, but that's the next rule. But don't be confused with that after the decimal. I mean, before scientific notation.
Right.
So an example of this that wouldn't be significant is if you had a 0 in front.
Right.
And like you had 1.0.
Right.
Oh, that's a number in front. This is a number in front, so that would be. So like
0.001.
Like that.
Right.
So since
those zeros
these are not significant unless we put a number in front. Now those zeros in between
become significant
because of that second rule. Right.
Right.
Okay. Number 13. I mean.
Number 4. Okay. Counting numbers.
Okay.
And defined constants. Counting numbers.
And
constants have an infinite number of sig figs. Have an infinite number of sig figs.
Okay. So what that means is, like, if we're doing a conversion factor in a problem, and we're converting, 16 hours, okay, here is a problem. I mean, here's our question. So we have 2 sig figs to start out with. And then we are going along here, and then I write in 1 hour, there are 60 seconds. This one has 1 sig fig, and so does this one.
Right.
But that doesn't change our answer to have 1 sig fig, because these are counting numbers right here, unless it's in the question.
Right, it has to be in the question.
Right. So counting numbers like this do not count for significant figures. We don't count those for our answer. All right, and number 5.
Okay. Zeros that act as placeholders are not significant.
Placeholders. What does placeholders mean? They're
basically
just kind of holding the place of another number. So if you have 12,000, these zeros are kind of just acting as just to hold this 12 out here in front.
To tell you that it's 12,000.
Right, or those little numbers, these guys right here, these are placeholders. Okay, we don't need these. We can put this into scientific notation, and this number and this number are still the same. And these guys right here were just holding the place of that number. So if we can put it out here and put it into scientific notation, we can see that these zeros right here are not significant. So this right here this 0 would be significant because it's between
But you want to go back to our rules.
Yep, two non-zero numbers, where these are not.
Right.
Now, if there was a number over here after the decimal, if there was a 12 here, 0.12, then these zeros would be significant.
Yep.
But there isn't. So these guys are just placeholders, so we use scientific notation to get placeholders out of the way. Same with these guys. None of these zeros are significant because they're just holding the place of this 435. Now, if there was a number out in front, this was 10.0000435, then all of these would be significant.
Yep.
Okay, but for this problem, without the 10, there's just 3 sig figs. That make sense? Okay, so we just have a couple rules about scientific notation that we want to talk about. Scientific notation is very important because of that last rule in significant figures, okay? And we'll use it a lot. So our first rule is to just figure out which zeros are significant.
Yeah, which ones are significant.
I forgot a what in there. Sorry. Figure out what zeros are significant. Okay, so if we have a number like 14,000,
right,
which zeros are not significant?
All 3 are not significant.
Yep, these guys. So we'd move this into scientific notation. It'd be 1, 2, 3, 4. So it'd be 1.4 times 10 to the 4th.
Right.
Okay, let's do another example.
How about the number 0.00030?
Couple zeros.
And we got a lot of zeros there before and after our non-zero number.
Is this one significant?
No, it is not.
Okay, how about these 3?
No, they are not.
Those are placeholders. Okay, we have a significant one, obviously the 3.
Right.
And then how about this 0 on the end?
Right, if we look back at our rules, that number is significant.
Right, because there's a number in front of it. So we would move this guy 1, 2, 3, 4.
4 again. Yep.
Yep, and it'd be 10 to the negative 4.
Right.
Because we made the number smaller.
It's a smaller number.
Or the way I like to think about it, or this is a rule. Okay. And then let's do one more.
Okay, how about 140?
Ooh, good one.
Alright, no decimal. Alright. We only have 2 significant numbers there. Okay, the 1 and the 4. The 0 on the end, alright, is not a significant number.
But you said the 0 on the end over here counted.
Right, but that was because we had the 3 in front of it, and it's after the decimal.
But this one has a 1 and a 4 in front of it.
Right, but they're not behind the decimal.
Oh, so there has to be a decimal.
Right.
Okay, so if there's a decimal here, that 0 would be significant.
It would be significant. It would become significant.
But since there's no decimal, it's not.
Nope.
Okay. How about, what if I did this?
Then it would become significant.
It would, right? Because now this 0 is a significant 0 because there's a number in front and it's to the right of the decimal.
Right.
And then this one becomes significant because this is significant and the 4 is significant.
Right.
I know, right? So this guy, 140, only has 2 sig figs. And this guy right here has 4 sig figs.
Mm-hmm.
Where this one obviously has 2. And this one has 2.
2.
Okay. Rule number 2 is what?
We go down to the capitals.
Yep, always.
Alright, always has 1 digit. Always has 1 digit, then the decimal. Then decimal.
Okay, I see this mistake. Oh my goodness. There we go.
There we go.
I see this all the time on tests. I see the 14.32 times 10 to the 4th or something like
No, that
this.
is not right.
Okay, because there's 2 digits here.
Right.
Okay, and sometimes it's easy to do because we're doing a calculation. You might get 14.32, and then you get 10 to the 4th, but then we have to move it. So then you would have to move this over 1. And so then it would be 1.432 times 10. Since you made this number smaller, you got to make this one bigger.
Yeah.
So then it would be 10 to the 5th, which is our next rule, right?
Okay, our third rule is if you are making the given number bigger, the exponent is negative. If you make the given number bigger, the exponent is negative.
So, an example of this would be
About 0.004320.
Alright, well, how many sig figs do we have in that just to quiz you?
We have 4.
You're so good.
I am
Good. So we have a couple placeholders here.
Right.
So we don't use these guys.
No, we do not.
And then there's numbers in front of this guy to the right of the decimal.
Right.
Which is very important. So therefore we have 4. So we can put this in scientific notation. So we'd want to move the decimal 1, 2, 3. So there's one number.
One number.
Then the decimal. So we'd have 4.32 times 10. So this number was very small.
Right.
Teeny.
It was a tiny small
and we just
number.
made it a whole number to 4.
Right.
So we've made it bigger. So your exponent has to be negative.
It has to be a negative.
So -3. Whereas if you have a larger number.
Right. Like, how about 2,000,000?
Okay.
343,000.
Good one. So this one, these zeros right here, they're behind numbers.
Right, but they're to the left of the decimal,
Left
which
of
there
the
is
decimal.
no decimal.
No decimal at all.
Okay, so that makes them placeholders and they're non-significant.
Okay, so let's get rid of them then with scientific notation. So our decimal would be here.
Right.
So we'd move it 1, 2, 3, 4, 5, 6. So it's going to be 2.343. So we just took 2 million and changed it to 2.
Right. So we made it smaller.
And so that's our other rule. If you make numbers smaller,
right,
exponent
yep,
is positive. Okay, and so we moved it over 1, 2, 3, 4, 5, 6. So it's a +6, showing them that's going to be a really big number when that one's going to be small.
Yep.
Because this number right here should always be the same as this number right here.
Yep.
Okay. All right. So I guess that concludes our bit about scientific notation. Tomorrow or this weekend, you'll be watching a video over how to add, subtract, multiply, and divide exponents. Perfect. All right. Have a great day.